Okay, let's see if you were able to use the patterns that we had found to correctly expand the following. So I'm going to scroll back up to our pyramid for a sec. If you were to continue on in another row, which would be a plus b to the 6, our coefficients would be 1, 1 and 5 is 6, 5 and 10, 15, 20, 15, 6, and a 1. So let's put those in place first. So 1, actually we can do the whole thing. So our coefficient, or first coefficient, will be 1, and a is going to start off to the power of 6, if you recall, and a is going to decrease by 1, like we said over here, as b increases by 1 starting at 0. So we will have no b in our first term. Our second coefficient was 6, and then a will decrease by 1 as b increases by 1. Next coefficient was 15. A decreases, b increases. Then 20 as a decreases and b increases. Then 15 again as a decreases and b increases. Then 6 as a decreases and b increases. And lastly we had a 1, and a has now decreased to an exponent of 0, and b has increased to an exponent of 6. Again, note how the sum of our exponents in each term stays as 6. So if I continued on the pattern of coefficients from here, this is going to get really messy. I will have a 1, then 7, then 6 and 5 is 21, 15 and 20 is 35, 35, 21, 7, and then another 1. So again, I'm just getting these numbers by adding up the two from above, from the left, and from the right. And again, the 1 is like, it's getting a 1 from the right and a nothing from the left, so still 1. So let's try expanding this one. We're going to have to squish it. So 1, a to the 7. Our next coefficient is 7. A will decrease, b will increase. Then 21, a to the 5, b squared. Then 35, a to the 4, b cubed. Then 35, a cubed, b to the 4. Then 21, a squared, b to the 5. Then 7a, b to the power of 6. And then 1 with our a's disappearing because I have an exponent of 0. And b to the power of 7. So good for you if you were able to get that. So again, building from the question in your last day's homework that was on Pascal's triangle, the coefficients in Pascal's triangle can be written in terms of combinations, so n choose r, that led to the formula known as the binomial theorem. So the binomial theorem is a theorem that gives us the expansion of any binomial to the power of a whole number. So the first coefficient would be n, which is our exponent. Choose 0, then n choose 1, 2, etc. until we get to n choose n, which is why we have a 1 on either end. And then here we see our a starting at the power of n, whatever your exponent is of your binomial, and then the exponent of a decreasing by 1 as the exponent of b is increasing by 1. So from 0 to 1 squared, etc., until a has disappeared and b is to the power of the original binomial. So this is not actually a formula that you will be given and that we won't actually be using. What we will be using is the general term. So the general term, you may remember hearing this word before. We've used general term when we were talking about like Tn, like the general term of a geometric series, or Sn for sum. In this case, we have a general term for binomial expansion. So we can actually get any term in the expansion without having to expand the whole thing. So the way this works is, let's say I want to find the fifth term. So I want t to be 5. I want to find the fifth term in something. If I want to find the fifth term, and my general term says my term is k plus 1, what should I plug in for k if I want to end up with the fifth term? Well, what plus 1 is 5. So I would use 4 here. And let's say I want to find the fifth term of a plus b to the power of 7, just because we have that up here. The fifth term is going to be when k is 4 and n is 7, right? N is my original exponent. So I would have 7, choose 4, then a to the power of n minus k, or 7 minus 4, and then b to the power of the k, which is 4. And if we look up here really quick and we count out our fifth term, 1, 2, 3, 4, 5, you'll see that if you evaluate 7c4 on your calculator, you'll get 35. 7 minus 4 gives us a cubed. And then we have b to the power of 4. So you can spotlight and figure out any specific term in an expansion without having to do the whole thing. This is less of an issue when we're working with an exponent of 7. Can be a way bigger issue when we're working with exponents that are greater than 14, etc. You can imagine that this can simplify your life a lot when looking for a specific term. The key is here that if you are looking for a fifth term, you must remember your k is always going to be 1 less than that, because our general term is represented by k plus 1. So let's do one example of that, and that will be the end of this segment. So let's try this first example. Oh, lo and behold, it's the fifth term that we're going to be looking for. So in this case, actually, I'm just going to rewrite the formula for us right up here at the top. So our general term, t k plus 1, is equal to n c k, a to the n minus k, okay, and then b to the k. Okay, so finding the fifth term, if I'm looking for t5, I should be plugging in k is 4 for the same reasons that I just talked about in the last example there that I made up. So if k is 4, my n is whatever this exponent is, so 8. N is 8. And now I'm just going to plug in. So n, 8, c, k, which is 4, a to the power of 8 minus 4, and then b to the power of 4. This gives me, if you evaluate on your calculator, this will give you 70, a to the power of 4, b to the power of 4. And there you have it. Feel free to try the next one and go ahead before checking on the video. Otherwise, I will see you soon.